Okay, we have a large tank with a pump that's pumping out the water through a pipe. This is a very, very similar problem to what we have in one of our classworks. I think it was like a week back or whatever. But in this case, we are taking into account of minor head losses. So the minor head losses are these sharp edges right here, and the way the water is exiting the pipe in this type of pipe cutout. I'm going to go over these two in a little bit, but first we're going to write down all of our given values. So our given, the height of the water, Z1 equals 6 meters. The diameter of the pipe is D 0.07 meters. The length of the pipe is 2 meters. L equals 2 meters. And the material that is used to make the pipe is cast iron. So let's go to our textbook. Cast iron, 0.26 millimeters. That's our roughness. I'm going to write that, so the symbol that's pronounced epsilon. So remember the E, so it's like a weird shaped E. E, roughness, 0.26 millimeters. You can convert that to meters, and that you go to 0.00026 meters. Let me check a little bit, actually. 0.026, 0.212. Yep, it is 0.00226. So our minor losses. Sorry about that. That was my phone. Use that as a light source. There you go. Now, minor losses. In my textbook is page 417, but if you guys have like a different edition textbook, it might be a different page. But this circled is what we have. We exact same edges, and it's going to be 0.5. Flip some more pages. Let me adjust it. There you go. This is the exact same type of pipe that we have. I mean, like, they're all going to be ones anyways, but I'm just trying to show you which category that we fall into for our problem. So that 1.0. Let's flip back some pages to the Moody diagram that we're going to use later to find our friction factor, which I'm going to go over. But we're going to start with writing down our minor losses. Sharp edge, KSE, 0.5. Exit of the pipe, 1.0. So let's start with the energy equation. You guys know what the energy equation is. V1 squared plus V1 squared 2G plus Z1, 6 meters, plus HP, our head pump equation. We're going to put that in later. P2, 1V2 over 2G plus Z2 plus head loss. So let's work from left to right. Head pump. 20 minus 2,000 volumetric flow rate square. That's going to be a part 1. That's what we're going to find later. But for now, pi, so flow rate equals pi over 4 dV. We're going to leave V alone because we don't have V right now. But we're going to put V into the equation, and we're going to separate V so that we can find V by plugging in the friction factor from the Moody diagram. So, pi over 4, 0.07 meters V. Plug the whole thing in. HP equals 20 minus 2000 pi over 4, 0.07 V squared. You multiply pi over 4 times 0.07. Let me see, you get 2000 pi over 4. 0.00, you get 0.00385. You leave V alone, square. Square the whole thing, multiply by 2000, and you will get, let's write over here, 20 minus 2000 times that part, 0.029645 V squared. So we're done with our left parts. We can go to the right. Let's go to our head loss first. So we can divide that. Head loss, we know the head loss equation. Head loss major plus head loss minor. Equational form. Friction factor L over D, length over D. V squared over 2G plus another V squared over 2G for the minor loss. And we've got to take into account of our sharp edges and our exit, KSE plus KEX, which is 0.5 plus 0.1. Move this page down. So minor loss, take into account 0.5 plus 1.0. We're going to plug in our L, which was 2 meters, plug in our D, 0.07 meters. So that's going to leave us with the equation. Plugged in the equation, frictional factor, which we didn't find, which we're going to find in a little bit, 2 meters, 0.07 meters, V squared over 2 gravity, again, gravity 9.81, we're going to plug it in later, another V squared over 2G, 1 plus 0.5, that's 1.5, and you divide 2 over 0.07, you're going to get, wait, hold on, yes, divide this, combine these two, take V squared over 2G out. So HL equals F, 2 divided by 0.07, that's 28.57143. Let me check. Yep. Plus 1.5, 1 plus 0.5. And you took the V squared over 2G out. You get this for the HL. So we're going to combine. I'm going to put HP right here. I'm going to put HL right there. You're going to put Z1, which is 6 meters, to the other side. So, oh wait, before we do that, we don't have pressure. Let's cancel that. We had no inertial velocity. Cancel that out. We had no 2Z. We had no Z2, I mean. Because we only have one height, Z1. So that leaves us with this, another V squared over 2G, and HL. I'm going to put that to the other side. So our HP, 20 minus 0.00385 296.45 v squared, that equals to F 28.57143 plus 1.5 v squared over 2g plus another v squared over 2g. I forgot to put the v2 on the bottom, but that's fine. They equal to each other. And minus, we put the z1 on the other side, so minus 6. So let's see here, 20 to the other side, get rid of the fraction, so u times this on the top by 2g, 2 times 9.81, 2 times 9.81, u times 2 times 9.81 to this side, and you also times 2 times 9.81 to this side when you put the 20 with the 6, and that gives you 26. 26 times 2g. So that's going to be 0.5816 v squared F 28.57143 v squared plus, oh, forgot to mention, another 2g. So this is 1. 1.5 plus 1, 2.5. So that's 2.5 v squared minus 6 plus 20, 26, 26 times 2 times 9.81, that's 510.12. You put all the v's on one side, put that on the other side, put the 510 on the other side, so you get 510.12 equals F 28.57143 v squared plus 2.5 plus, just trying to simplify this, you know, so we can make it more organized. 2.5 plus 0.5816, so 3.0816 v squared. And then you're gonna get, what are you gonna get this? Let's put that in the new page. You're gonna get, you put v squared, the 510. See if I can balance this. 510.12 F, divide all that stuff to the bottom, 0.57143 3.0816. So this is all we can do for now, because we're gonna go find the friction factor with the Moody diagram. So for the friction factor, okay, let's hold this up a little bit. Epsilon, which is given, which was what, 0.00026 meters, and our diameter was 0.07 meters. So we're gonna find this first, and that will get us, so a ratio of 0.00026, 0.07. Our ratio is going to be 0.0037. Now, go back to the Moody diagram. 0.0037 is very close to 0.004. So, and the problem stated that it is fully turbulent. We're going to prove that in a little bit with the Reynolds number. But for now, we're going to assume, since that's what's stated in the problem. So anything that's, well, for the Moody diagram, the easiest way to tell is that we're just going to follow the flat lines. This is fully turbulent. Right here, anything to the right is fully turbulent. That's where it starts, fully turbulent. Starts, fully turbulent. So 0.0037, very close to this line. We're going to follow this line all the way to the left. We get to this point. So we can, let's bring this up. 0.025, we're just going to say that's 0.026, 0.027, and 0.028. 0.0037 is slightly below 0.004, so we're going to assume that our number for our friction factor is going to be slightly lower than 0.028. So I think if you write down the friction factor to be 0.0278, that will work pretty good. So if we got our friction factor, we got our simplified, let's move this down, energy equation, plug this in, find the velocity. Because we need the velocity for A and B. A as in our volumetric flow rate, which is going to require the V, and B, our Reynolds number, which is also required the V. And we need the Reynolds number to prove that this is a fully turbulent flow. So V square equals 510.12. F is 0.0278. 28.57143 plus 3.0816. Let's see here. Square root the entire thing. You get V equals 11.47225 meters per second. So we got the B, and now we can go on and solve A, B, and C. So let's start with A, our volumetric flow rate, which was Q. And if you look back to our previous notes, where is it? Oh. Right here. 0.00385 V. That's our volumetric flow rate. Write that down. Q 0.00385 V. We know V, we're going to plug it in. 0.00385, 11.47225. Flow rate's going to be 0.004417 meters cubed per second. That's our unit. That's going to be part A. Part B, Reynolds number equation, rho VD over U. Rho, we know, is 1000. And U is going to be 10 to the negative third. So we know the V is 11.47225, and we know our diameter of the pipe 0.07. That's going to give us a Reynolds number, and our Reynolds number is going to be 800,000, 3,057.5. That is way bigger than 4,000. And if anything that is bigger than 4,000 is a fully turbulent flow, so that checks out. So Good. Last part, C. We are going to use the power equation with consideration of the 70% efficiency. So, W dot, you got the usual rho GH, put Q in the back, 0.7, 70%, 0.7. 1,000, that's rho G, 9.81, gravitational unit. H, we have it in our last page, which is, there you go, 20 times 2,000, wait, not this one, 20 minus 2,000, plug in V. We are going to get Q. Oh, sorry about that. Nope, that's not that one. It's this. Since we got the Q already. 20 minus 2,000 times Q. Q is 0.00417. So we're just gonna plug that in here. Perfect. Okay. So 20 minus 2,000 RQ, 0.004417 squared, parentheses, another Q on the outside, 004417 all over 70% efficiency, 0.7, and we're gonna get our power in watts, which we're gonna convert to kilowatts. So that's gonna give us 9,900. Wait, 9,965 watts. That's gonna equal to 9.97 kilowatts. Okay, here you go. Thank you for watching.